All right, so yesterday we took a formative on molarity and solubility. So if we look at that first, um, we're going to go through this one pretty quickly, but if you have questions, just stop me, raise your hand, just let me know. So the formative was on 4.3, so it was mostly molarity, but you also need to do for every problem is to make sure you are checking to see if the solutions are soluble or insoluble. If the solution's insoluble, you can stop right there. Don't worry about it. Ignore it. Say it's insoluble, and then you are done. There's no math involved. There's no nothing. As soon as you see that it's insoluble, you are done with that problem. So we look at that first one. It says you are given 14,722 milligrams of barium chloride and 90.0 milliliters of water and asked to make a solution. What is the molarity of that barium chloride solution? So the first thing we're going to do is we're going to check that solubility, and you're going to find out that barium chloride is soluble. So barium chloride is soluble. So we do have to complete this problem because barium chloride is soluble. So then we're going to look back at the problem and we're going to see that we were given 14,722 milligrams. And we were given 90.0 milliliters of water to make this solution. The first thing we want to do is just to make sure all of our units are the correct units to solve any problem. So if we have to do conversions, let's do those right away at the very beginning. Let's not worry about them for later. So this first one, we have milligrams, and we know we always want our mass for chemistry class to be in grams, which means we are going to convert. So I'm going to draw my lattice structure, my railroad tracks, and I'm going to put that 14,722 as my given in milligrams. Now I want to get rid of milligrams, which means my units of milligrams go on the bottom. And we should remember from the beginning of the semester that 1,000 milligrams is equal to 1 gram. Which means I'm going to multiply my 14,722 times the 1, and I'm going to divide it by the 1,000, and we should figure out that this is really 14.722 grams. So our mass is really 14.722 grams, not the 14,722 milligrams. The next one we're looking at is that 90 milliliters of water. When we're making our solutions and we're talking about molarity or concentration, we always worry about our volume to be in liters. So we're in milliliters here, and we want liters, which means we have to convert that as well. So I'm going to set the second one up. And for this one, I'm going to put my 90.0 milliliters on top. Just like our milligrams to grams, our milliliters, there are 1,000 milliliters in 1 liter. So when we do this, we have 90 times 1 divided by 1,000 gives us our answer of 0.0900 liters. Remember, we want to keep those significant figures, and because there's that decimal point right there, that makes these 2 zeros significant, which means we have 3 significant figures here, and this one has 5 significant figures here, just like in the original value. So when we're solving for things at the end, we got to make sure our significant figures do in fact stay the same. The next thing we have, we're looking for that molarity. And so we're looking at this problem. We can see that we have grams and we have liters. We know that molarity is moles divided by liters, which means we have to get our grams to turn into moles. To do that, we can figure out the molar mass, which tells us how many grams equals 1 mole of that compound. So the first thing we need to do is find the molar mass. So if I find the molar mass, I'm going to find the molar mass of barium, and I'm going to find the molar mass of chlorine. because those are my two compounds or two elements in the compound. When I find my molar mass of barium, I found it to be 137.33. If you have 3 decimal points, that's fine. Just the periodic table that I normally use, just because it's closest, only has 2. If you want to round to 2 every time, that's fine too. It's up to you. But my chlorine, I found my chlorine to be 35.45 grams. But my barium chloride, if I remember from getting this formula, barium normally has a +2 charge because it wants to lose 2 valence electrons, while chlorine has a -1 charge because it only needs 1 valence electron to have its full octet, which means we need 2 chlorines for this compound, which means I need to multiply this Cl by 2. So when I multiply that by 2, I can now add all of this together. And when I add all of this together, I'm going to find that my value is 208.23 grams of barium chloride is equal to 1 mole of barium chloride. So my molar mass is really a conversion factor, or a way for me to get from grams to moles or from moles to grams. So now that I know my grams and I know my conversion factor, I can now set up my railroad track just one last time. This time, taking my number of grams of 14.722 grams of barium chloride. And I'm going to convert using my molar mass, making sure that my grams go on the bottom down here. So my 208.23 grams of barium chloride, which means this is 1 mole of barium chloride on top, because our grams cancel out, and we are looking for those units of moles of barium chloride. So if I solve this, I have 14.722 times 1 divided by 208.23. And when I solve this, I should find out that my number of moles is 0.070701 moles of barium chloride. Remember to make sure your sig figs are in every problem. So we look at our given. We should have 5 significant figures from here, which means if we count, we have 1, 2, 3, 4, 5. Because that 0 in front, these 2 zeros do not count, but these 2 zeros count. Lastly, I have moles and I have liters, and I'm looking for molarity. So my molarity equals the moles divided by the liters, which means my molarity equals my 0.070701 moles of barium chloride divided by my 0.0900 liters. And when I solve this, I should get a value of 0.786 molar of barium chloride. And we only have 3 significant figures because we have 3 from our volume, which is lower than the 5 from our moles, which means we use the 3 from our volume. Any questions on that first one? All right, so the second one, I apologize for that second one first, just because potassium chromate wasn't on your solubility chart, so you might have had to look that one up. And I apologize for that, just because of the fact that if you didn't have to look it up, it would have made your life just a little bit easier. So if we remember potassium chromate, so potassium is K with a +1 charge. Chromate is CrO4 with that -2 charge, which means potassium chromate is K2CrO4. and it's going to be soluble, which means we have to do this problem. So now let's look at our information. It says you're asked to make 122.560 milliliters of a 1 molar solution of potassium chromate. How many grams of potassium chromate do you need? So we have the milliliters and we have the molar solution. The first thing we should notice is milliliters instead of liters, which means we do need to convert. So if we set up our conversion, we have our 122.560 milliliters. From before, we noticed that 1,000 milliliters was 1 liter. So when we solve this, we have 122.560 times 1 divided by 1,000 gives us our 0.12256 liters. Since this 0 is after a decimal point, it does count as a significant figure, which means right here we have 6 so far. Not what I wanted to do, I apologize. All right, so now our next step is we have the liters and we have the molarity, and it wants us to find the grams. But liters and molarity, the only thing we can get from there is we can go to moles, which means we are going to use our molarity equals moles over liters to solve for the number of moles. So we can set up this problem as 1.000 equals the number of moles divided by the 0.12256. To get the moles by itself, we are going to multiply the volume or the number of liters to both sides. When we do that, these cancel over here, and we are left with the number of moles, which equals 0.1226 when we round to significant figures because of our 4 significant figures in our molarity. So this is our number of moles. Now that we have our moles, we can now get to grams by using the molar mass. So we first have to find that molar mass. And if we are looking for our molar mass, we need to look for our molar mass of potassium, chromium, and oxygen. We can find the molar mass of potassium to be 39.10. We can find the molar mass of chromium to be 52.00 and oxygen to be 16. We have 2 potassiums in our compound, so we multiply our potassium value by 2, and we have 4 oxygens, which means we're going to multiply our oxygen value by 4 to find our molar mass. When we add all those values together, we are going to get 194.20 grams of potassium chromate equals the 1 mole of potassium chromate. We're going to use that to solve for our number of grams. So if we set up our railroad tracks, our lattice structure, we're going to take our given, which is going to be the moles. So the 0.1226 moles of potassium chromate. And we're going to use our molar mass as our unit conversion, which means we are going to put the moles on the bottom so that they can cancel out, which means 1 mole goes on the bottom. And that means the mass of 194.2 goes on the top. So when we solve for this, we are going to take our 0.1226 times 194.2 and divide all that by 1 to get our value in grams, because it's the only unit left, grams of potassium chromate. which gives us 23.81 grams of potassium chromate based on the 4 significant figures in our problem. And then know those masses. So my masses have 2 decimal points. If yours have 3 decimal points, that does not affect the problem. If you got a value of like 23.80 instead of 23.81, it does not affect your problem. Usually when we're doing these problems, if we're in person, we would actually get masses or balances out and we put our values and we'll get our grams. Usually within a 5% error or within like 0.5 grams here or there, so up or down. It isn't going to affect your data enough where it's going to be inaccurate. So no, it's okay if your values round to different values for your molar masses, but make sure your significant figures in the end of your problem do in fact have the correct number of significant figures of 4 significant figures for the problem. Any questions on 2? All right, so the last one is magnesium phosphate, which is Mg3PO4 And if we look at our solubility chart, we are going to find out that this is insoluble. And so we're done. Don't do anything else for that problem. If you show me work for that problem, I will mark it wrong, and that will make you lose points. So showing work for this problem is going to be bad because it's insoluble, which means it will not happen. Are there any questions on 1, 2, or 3? All right, so then before we do anything else, I'm going to scroll down just a little bit just so we have some room. I do want to refresh our brains about intermolecular forces because those formatives on Monday didn't look perfect, which we do have our summative, and it's going to have molarity, solubility, and intermolecular forces, which I know is something that like we haven't done a whole lot with since probably Tuesday. I think we talked the last time about it, which means that we probably need to go through them just one more time. So if we look at intermolecular forces, we have 4 intermolecular forces that we kind of talked about, 3 big ones, and then there is one that's kind of, or 1 or 2 that are kind of just there that we should know. The first one, probably the easiest one in my opinion, is going to be ion interactions. And that's the easiest one in my opinion because it only happens with ionic compounds, and it's only when ionic compounds are by themselves. And that's because the ions, so we know that if we have sodium chloride, we don't just have 1 sodium and 1 chlorine. We have a bunch of sodium ions and a bunch of chlorine ions, and they're going to be like interlocked next to each other. So if I have my first sodium ion here and my chlorine ion here like this, then the next salt compound is going to have the sodium like this and the chlorine like this, so that our ions have some interaction between one another. They're not bonded like the sodium and the chlorine are that are in the same compound, but they do have an interaction, and that's why we have those structures that stick together like our table salt. The next one is going to be ion dipole. And so if we remember, dipoles are those polar covalent molecules that have a partially charged positive side and a partially charged negative side. And so this really just happens when we have ions or ionic compounds like salts and other ionic compounds that get dissolved into something. So our solutions, that's when we get those ion dipoles, because the ionic compound will break apart so that the ions, so the separate ions, we'll have interactions between the dipoles. So if we think back to our sodium chloride, when it separates, because it dissolves in water. So if I have my H2O, so my oxygen molecule like this, oxygen, water is a polar molecule because we have a partially charged or partially negative charged oxygen and partially positive hydrogens. So we have our partially charged parts of our polar molecule because oxygen has a larger electronegativity. Our sodium, when it breaks apart, we're gonna see our sodium form an attraction to our oxygen because it has that negative and the positive are going to attract towards one another, and our chlorine is going to attract towards our partially positive hydrogens. So that negative attracts towards the positive attracts towards the negatives, and that's why if the attraction between them is strong enough, there's going to be that breaking of the bonds. That's why the ion will dissolve because of that intermolecular force. The next one we're going to talk about is dipole-dipole. And that happens when we have two polar covalent molecules together, or the multiple polar covalent molecules. So if I have a bunch of hydrogen and chlorines bonded together, chlorine has a much larger electronegativity, which means it's going to have the partial negative. Hydrogen has the partial positive, and then another hydrogen and chlorine come in. And so this partial positive is going to have that intermolecular attraction or intermolecular force trying to attract that hydrogen to the chlorine. And this one has that partial negative charge. So if I had a third one, we'd see another attraction between that chlorine and that hydrogen. So the dipole-dipole is just between polar covalent molecules. It can be the same one just multiple times. It can be two different polar covalent molecules. It doesn't matter. As long as they're polar covalent, you would see that attraction. Then the next one is going to be, or the specific dipole-dipole is going to be hydrogen bonding. And that only occurs in three types of bonds. If you have an N bonded to an H, if you have an O bonded to an H, and you have an F bonded to an H. These are going to be stronger than any of our just normal dipole-dipole interactions. And that's because of the large difference in electronegativity. These three have a much larger attraction or interaction than anything. So if we look between the polarity difference between chlorine and hydrogen is larger than nitrogen and hydrogen, but nitrogen forms this hydrogen bond, which means it's going to have larger interactions, even though it is slightly less polar than our chlorine. So these three have hydrogen bondings. They're very specific and they're very strong. And those are just the polarities are just so large between those three, it causes just a greater attraction. It is the reason why we have these as liquids rather than as gases when we're talking about like things like water. Water would technically be a gas, but the hydrogen bonding, that interaction between our O's and H's in different molecules of water, keep those water particles together, which is why it stays a liquid, which is why we have water to drink. The last one is going to be our London dispersion force. You're going to see there's lots of different names. There's a video that goes through all this again on Canvas. It's called Intermolecular Forces Review. They call it van der Waals forces. It's also called just dispersion forces. So this can be gotten rid of depending on where you look. Dispersion force, London dispersion force, van der Waals forces, they're all the same thing. And it just means that there is an induced dipole. And what induced dipole means is that even non-polar molecules, so any molecule, polar, non-polar, any of them, like if we look at hydrogen and hydrogen, we know that there's two valence electrons that are floating around in between those two to hold them together. And an induced dipole at one particular snapshot, if we're looking at it for just 1 second, if we bring in another hydrogen-hydrogen bond, we bring them close to each other, what's going to happen is the electrons for 1 second potentially could move towards one of those hydrogens. So the electrons over here, if we have our two electrons instead, they slid over so they're closer to this hydrogen just for one instance. They're closer to this hydrogen than the second one. Then in this one, the electrons are going to try and slide over here so that there can be an interaction between our two molecules. So they're going to induce or create, they're going to create a dipole for a moment to make this interaction. So this is between all molecules. So no matter what, there has to be London dispersion forces. There can be London dispersion forces and dipole-dipole. There can be London dispersions, dipole-dipole, and hydrogen bonding. There can be all of those, but there has to always be those London dispersion forces. Are there any questions on those intermolecular forces? I know we just went through them pretty quickly, so do you guys have any questions? All right, then the last thing you guys have today is your review for your summative tomorrow. So there's going to be some multiple choice questions, just like there are here. And then there are some questions just like your formative from yesterday, some molarity questions, making sure that you are checking for solubility and making sure that you are using that dimensional analysis. So make sure you use that lattice structure and make sure you're checking for sig figs. On your summative, if I don't see these or I don't see you using sig figs, you are going to lose points. So make sure you're using that conversion method, or that you're showing your work at least for those conversions that you're doing or those calculations you're doing, and making sure that those sig figs are